There is a machine on this planet that costs more than a Boeing 747, takes years to build, requires more than 100,000 individual components, and must operate with a precision measured in billionths of a meter. And every single chip inside your AI assistant, every frame rendered in a modern video game, every autonomous vehicle decision made in a fraction of a second, they all begin their lives inside this machine. NVIDIA's most advanced processors contain over 80 billion transistors packed into a piece of silicon smaller than your thumbnail.
If you tried to count each one at a rate of 1 per second, it would take you over 2,000 years. By the end of this video, you'll know exactly how it's made. We are living through one of the most significant technological shifts in human history, and at the center of it sits a tiny rectangle of engineered silicon. NVIDIA chips don't just power video games anymore. They run the models behind ChatGPT. They train the AI systems that diagnose cancer. They simulate protein folding, climate models, and financial markets.
The global GPU market is now worth over $200 billion and is growing faster than almost any industry on Earth. In 2023 alone, NVIDIA's market capitalization surpassed $1 trillion, making it one of a tiny handful of companies in history to reach that milestone. And yet, almost nobody outside the semiconductor industry has ever seen how these chips are actually born. The process is so secretive, so technically demanding, and so extraordinarily complex that even the people building the factories don't always understand every stage. This is the story of how sand becomes the most powerful computing device ever created. Everything begins with one of the most abundant materials on the planet, silicon. Silicon is the second most common element in Earth's crust, found in ordinary beach sand and desert rock. But the silicon used to build NVIDIA chips is nothing like the sand on your beach. It must be the purest substance ever manufactured by human hands.
The standard is called 9-9's purity. That means 99.9999999% pure silicon. A single foreign atom in the wrong place can destroy an entire chip. To achieve this, raw silica rock is mined primarily in regions of the United States, Brazil, and Australia. It's then processed through a series of chemical reactions that strip away every impurity. The result is a dense, silvery material called polysilicon, which is then melted down at temperatures exceeding 1,400 degrees Celsius inside a quartz crucible. Here, a single seed crystal of pure silicon is dipped into the molten material and slowly rotated and withdrawn over dozens of hours. The result is a perfect silicon cylinder called an ingot, sometimes nearly 2 meters tall and weighing over 100 kilograms. From the outside, it looks like a large metallic sausage, but inside, it is a flawless crystalline structure aligned at the atomic level. Every atom precisely in place, every defect essentially zero. That ingot is then transported to a specialized facility where it's sliced into wafers using diamond-coated wire saws.
Each wafer is thinner than a human hair, just about a millimeter thick after slicing, then polished down to a mirror finish so perfect it reflects like glass. The surface must be smoothed to within a fraction of a nanometer. Think of it this way. If you scaled a finished wafer up to the size of a city, the tallest imperfection on its surface would be less than 2 centimeters high. It would be the flattest landscape on Earth by a significant margin.
These wafers, typically 300 millimeters in diameter for advanced chips, are then packaged in sealed nitrogen containers and shipped to fabrication plants. Not just any fabrication plants, the most advanced manufacturing facilities ever built. NVIDIA does not manufacture its own chips. This is one of the most important strategic decisions in the history of the technology industry. Instead, NVIDIA designs the chip in extreme detail, down to every single transistor, wire, and logic gate, and then hands that design over to a company called TSMC, the Taiwan Semiconductor Manufacturing Company.
TSMC is the most advanced chip manufacturer on Earth, and it builds chips for Apple, AMD, Qualcomm, and dozens of others. The reason NVIDIA doesn't build its own fabs, as these factories are called, is simple. A single advanced semiconductor fabrication plant costs between $15 and $30 billion to construct. It requires years to build, a decade to master, and a workforce of thousands of specialized engineers.
It is, by almost every measure, the most complex manufacturing environment humans have ever created. TSMC's fabs in Taiwan operate 24 hours a day, 7 days a week, 365 days a year. And inside them, something almost miraculous takes place. The wafer arrives at the fab, sealed in a special container called a FOUP, a front-opening unified pod. It looks like a white plastic lunchbox, but it maintains a near-perfect internal atmosphere and protects the wafer from contamination. Inside the fab, these pods are carried around by automated rail systems above the production floor, a network of vehicles that move without any human intervention, silently gliding through the air like a miniature train system in the sky. The production floor itself is a clean room. Not a clean room in the way a hospital is clean. This is Class 1 clean, meaning there are fewer than 1 particle per cubic foot of air at any time. For context, the air you're breathing right now contains roughly 100,000 particles per cubic foot at any time. The air inside a TSMC fab is 100,000 times cleaner than that. Workers wear full body suits, called bunny suits, that seal off every inch of their skin and hair. Even the exhaled breath is filtered. Because a single microscopic particle landing on a wafer at the wrong moment can render a chip useless. Now, the real magic begins. The process that transforms a blank silicon wafer into a chip is called photolithography, and it is without question one of the most remarkable engineering achievements in human history. Here's what happens. The wafer is coated with a light-sensitive chemical called a photoresist. Then, an extraordinarily precise light source is shown through a mask, essentially a stenciled template of the circuit design, onto the wafer surface. Where the light hits, the photoresist changes its chemical properties. The exposed areas are then dissolved away using special chemicals, leaving behind a precise pattern etched onto the silicon. This pattern defines where transistors, wires, and connections will be placed. Then the process repeats, and repeats.
And repeats again. For NVIDIA's most advanced chips, this process happens over 150 times. Each layer is aligned to the ones below it with a precision of less than 5 nanometers. And this is where things get truly extraordinary. The machine that performs photolithography is called an EUV lithography system, and it is built by a single company in the world, ASML, headquartered in the Netherlands. There is no second source. There is no backup manufacturer. Every cutting-edge chip on Earth, from Apple's iPhone processors to NVIDIA's AI accelerators, is made using machines that come from one factory in Veldhoven, a small Dutch city most people have never heard of. ASML's EUV machine, the high-NA EUV system, costs approximately $380 million per unit. It weighs over 180 tons. It contains over 100,000 individual components. It uses a laser the size of a room to generate plasma that produces extreme ultraviolet light, a wavelength of just 13.5 nanometers, shorter than X-rays. This light is reflected off mirrors polished to within a fraction of an atom, then focused down through a lens system onto the wafer to draw features just 2 nanometers wide. To understand how small that is, a single strand of human DNA is about 2.5 nanometers wide. NVIDIA's chip transistors are smaller than DNA. Let that sink in for a moment. But photolithography is only one piece of this process. Between each patterning step, the wafer goes through dozens of other treatments. Ion implantation fires charged atoms into the silicon at near light speed to modify its electrical properties in specific zones. Chemical vapor deposition builds up incredibly thin layers of materials, Metals, insulators, semiconductors, one atomic layer at a time. Plasma etching uses ionized gases to carve features into the silicon with atomic precision. Annealing heats the wafer to high temperatures to fix the crystal structure after implantation. Each stage must work perfectly. A mistake at layer 50 doesn't just affect layer 50. It cascades down through the remaining 100 layers, potentially making the entire chip worthless. This is why yield, the percentage of working chips produced from a single wafer, is one of the most closely guarded metrics in the semiconductor industry. For the most advanced chips, early yield rates can sometimes be below 50%. Every failed chip represents thousands of dollars of lost material, energy, and machine time. After photolithography and all related treatments are complete, the wafer contains hundreds of individual chips arranged in a grid, each one a complete processor. But they haven't been tested yet, they haven't been separated, and at this stage, they're still just patterns of silicon, metal, and insulator. The wafer now moves into what's called the back end of line process, where the chip's wiring is completed. Modern chips have up to 15 or more layers of metal interconnects stacked on top of each other, a microscopic three-dimensional highway system carrying electrical signals at the speed of light across billions of pathways. Each layer is deposited, patterned, and connected to the ones above and below it through tiny vertical pillars called vias. The complete wiring network in an NVIDIA H100 data center chip contains more than 10 kilometers of metal wire, all compressed into a chip the size of a postage stamp. Here comes the part most people never think about. Once the chips are fabricated on the wafer itself is destroyed. It's sliced apart using diamond-tipped saws and lasers in a process called dicing. Each individual chip, now called a die, is separated from its neighbors. The dies that pass initial screening are then bonded onto a package substrate, a small printed circuit board that provides the electrical connections to the outside world. For NVIDIA's most advanced products, like the H100 and the newer Blackwell architecture chips, this packaging step has become nearly as complex as the chip fabrication itself. Multiple dies are bonded together using a technology called chip-on-wafer-on-substrate, or CoWoS. High-bandwidth memory modules are stacked alongside the processor die and connected through thousands of microscopic copper pillars called microbumps. The entire assembly is then encased in a protective material called molding compound. The final package looks like a large green square, nothing special to the naked eye. But inside, it contains more engineered complexity than almost any object humanity has ever created. Now, quality control. Every single chip that comes off a production line is tested, not sampled, every single one. Automated test equipment, machines the size of refrigerators that can cost millions of dollars each, probe every electrical contact on the chip and run thousands of diagnostic routines. They verify logic function, memory integrity, power consumption, and performance at multiple clock speeds and temperatures. Chips that don't meet the full specification aren't automatically discarded. Some are binned down to lower product tiers, sold as slower or less fully featured chips under different model names. This is why NVIDIA can offer a range of products from the same manufacturing process. A chip that fails memory testing in a small section might still work perfectly as a lower-end product. The testing facilities run continuously, processing thousands of chips per hour. For every 100 chips that begin the journey as blank wafers, roughly 60 to 70 will make it to final sale as a functional product. And that number for the most advanced nodes represents an extraordinary achievement. Now here are the numbers that will genuinely change how you think about this industry. A single TSMC fab facility produces approximately 100,000 wafers per month. Each wafer can yield hundreds of chips, depending on the die size. NVIDIA's data center chips, being large, yield fewer per wafer, sometimes fewer than 60 on a 300mm substrate. That means one fab produces roughly 6 million data center class chips per year at full capacity. The energy consumption of a single advanced fab rivals that of a small city, consuming hundreds of megawatts continuously.
Building one fab takes between 3 and 5 years from groundbreaking to first production. TSMC currently employs over 70,000 people globally, with thousands of PhD-level engineers focused solely on process development.
The amount of water a fab uses in a single day, primarily for ultra-pure rinsing processes, can exceed 10 million liters. And NVIDIA's design team spent over 4 years and billions of dollars designing the Blackwell architecture before a single chip was ever manufactured. The global supply chain behind every NVIDIA chip is staggering. Silicon comes from the Americas and Australia. The EUV machines come from the Netherlands. Specialty chemicals used in photolithography are produced in Japan and Germany. The high-bandwidth memory is made in South Korea by Samsung and SK Hynix. The substrate packaging happens in Taiwan, Japan, and increasingly in the United States. Final assembly and testing occurs across multiple Asian facilities, and then the chips are shipped in temperature-controlled air freight because sea shipping is too slow for a product worth tens of thousands of dollars per unit, to server farms in the United States, Europe, China, and the Middle East, where they are bolted into racks and begin running the AI models and computational workloads that are reshaping civilization in real time. There is a remarkable poetic arc to this story. It begins with grains of silicon pulled from the earth, processed through some of the most chemically intensive industrial operations ever devised. It moves through a factory where the air is cleaner than an operating theater, and machines operate at tolerances smaller than the atoms they're manipulating. It involves a global network of suppliers, scientists, engineers, and logistics networks spanning 15 countries, and it ends as a small green rectangle carried in a data center rack, running a model that writes poetry, discovers drugs, designs buildings, and holds conversations with billions of people. A single NVIDIA H100 chip sells for roughly $30,000. You could buy a new car for the same price, but nothing a car has ever done compares to what happens inside that rectangle every second it runs. What surprises you most about how these chips are made? Drop it in the comments. We read every single one. And if you want to go deeper on the supply chains, technologies, and factories shaping the modern world, hit subscribe. We cover the most extraordinary industrial stories on the planet, and we're just getting started.